Welcome back. So does anybody have any questions about the last time? I'm going to pick up in the middle just to remind you where we were. We were talking about the sparse pattern or the sparse dwarf, but there's also homework you could ask about. Razvan's always happy to answer questions about that, and Aditya. Okay, so let me just remind you what we had done last time. I was in the middle of telling you about sequential optimizations, and so here's the list. Today we're going to do all the parallel stuff. After I do one more example of putting all these sequential optimizations together. So we talked about how do you take your sparse matrix and organize it to make it run fast on a sequential machine where it's too slow if you store an index for every non-zero in the matrix. That's CSR format. So we talked about blocking the matrices, finding little dense blocks in the matrix, even if you have to fill in a lot of zeros. That can go a lot faster, up to 4 times faster. Sometimes it's hard to pick one block size into which to break up your sparse matrix, so you might have variable block sizes. Some matrices naturally have long diagonals that you can store as long diagonals with no extra indices. The example I'm going to show you right now is, right after this slide, is that sometimes you look at your matrix and there are no little dense blocks to take advantage of. But if you reorder the rows and the columns, you can make lots of dense blocks and go a lot faster. Now that's going to change your matrix representation in your higher level algorithm, but we can deal with that. I'll show you. Then there's symmetry. That obviously can save you a factor of 2 in how much data has to move back and forth, which is the big bottleneck, but sometimes it can save you even more. Cache blocking. So register blocking is sort of for one level of the memory hierarchy. Sometimes cache blocking is a good idea too. We use that for matrix multiply. And of course, if you have lots of vectors, then it becomes more like not matrix vector multiply, but matrix multiply. And we know there's lots of optimizations there, and there's a factor of 7. And then what I'll spend most of my time on today after I parallelize it all is higher level optimizations where I can get a lot of reuse and go much faster, not by computing just A times X, but by computing a whole sequence of matrix vector multiplies. Now, what is that particular kernel good for? Well, you have to reorganize all the solvers to take advantage of it, and I'll show you. But let me just show you one more example where I put all these together to do an optimization to show you what it looks like. And so this is an example we got from a collaborator who works at a national lab, and they were designing a next generation particle accelerator. And sparse matrix vector multiply was one of the bottlenecks in their simulation. So I'll show you a picture of the matrix in the next slide. So there's symmetry, take advantage of that. Register blocking, natural. But there are no little dense blocks in this matrix. We had to create them, and we created them by reordering the rows and the columns. And there were two graph theoretic techniques we used to do that. The first one has a long historical name, reverse Cuthill-McKee, but it's basically breadth-first search. You take the graph that is represented by the matrix, you do breadth-first search, and you reorder the rows and columns in reverse order that comes out of breadth-first search. That gives us a speed up, but there's actually something even better than that called the traveling salesman problem. So then we say, well, what if I were to jiggle the columns, reorder them, to put 2 columns side by side if they shared a lot of non-zero rows, right? That would create more blocks. So what I'm going to do is I'm going to create another matrix, another graph, where there is one vertex for each column, and there's an edge between 2 columns which says how many non-zeros do you share in the same rows. And so what I'd like to do is find a path through that graph which maximizes along each edge all the number of common non-zeros. That's something called the traveling salesman problem, which is a classical problem. And we'll see that when we put it all together, we get a 2x speed up. But let me go into the picture. So here's the original matrix. And so what I'm going to do is I'm going to take that graph and do breadth-first search and reorder the rows and columns in reverse order. And when I do it, it looks like this. So you can see that I've pushed all the non-zeros very close together. So it's going to be no surprise when I zoom in a moment that there are a lot more little dense blocks than there were before. So why does it look like this? Well, remember when we do breadth-first search, where are all the edges? There are edges from one level to the next. There's edges within a level. And then there's more inter-level edges that aren't in part of the tree, but they only go from like level 3 to level 4. So let's suppose I take a matrix and I order it so that I do all the levels 1 first, then all the level 2 nodes and all the level 3 nodes. Where can the edges be? They can only be inside the diagonal block that corresponds to one level, or they can go between adjacent levels. That means the matrix is block tridiagonal. So that's what that looks like. That's actually a block tridiagonal matrix. Yes?
Does it matter which node you pick as your...
No, you can pick a random starting node. I mean, some may be better than others, but in principle, you pick any old one. So let's go zoom in and see what happens. So here is, I've zoomed in the leading 100 by 100 before I've done any reordering. And so now I'm going to show you what happens after I reorder. And I'll have sort of color coding so you can tell the difference. So before, the nodes are colored green and red. And so the green nodes are there and the red nodes are all scattered. And after I do the reordering, the green nodes haven't moved, but the red nodes have turned into the blue nodes. And you can see they're now all of these dense blocks that weren't there before. The reds are scattered and then the blues are all collected. So that's the first step, reverse Cut-Hill-McKee, breadth first search. The next step is traveling salesman. So I'm going to toggle between, those two matrices aren't going to differ too much, so let me toggle between them. So now let me take this and do traveling salesman. That's what it looks like. And so let's just look at a few pieces. That has a lot of empty space in the middle of it, but when I do traveling salesman, it turns into one big dense block. There's one dense block, and before that they were apart. All right, that's a little thing, but that's what traveling salesman does. So what happens when I take that and I use it? What speedups do I get? So here's some examples. And so the vertical axis is speed up compared to the non-symmetric code, where I've blocked it as well as possible. So I'm picking the best block size. So that's speed up 1, that's horizontal line. And then these other dots tell me what are the benefits from doing, for example, symmetry with blocking. So I take symmetry into account, but I'm not reordering. That gives me the little blue square. What happens if I do traveling salesman but I don't take advantage of symmetry? That doesn't necessarily help at all. But what happens if I do everything, that example I showed you? So I take advantage of symmetry and then traveling salesman plus breadth first search plus blocking. That gets me up to here with speedups of like 2 and 3 and 1.5 and so forth. And so those are the benefits that you get on all these different computing platforms. So the question you may now ask is, okay, you've changed the matrix. By reordering it, how does that affect my higher level algorithm? So what is that going to do to the math and the rest of it? And so it turns out we can sort of factor the higher level algorithm to sort of almost completely hide the cost of the permutations. And so let me let A be my original matrix, and A super P be the matrix with permuted rows and columns. So the naive thing to do is just think of one subroutine, sparse matrix vector multiply. How am I going to use it? I'm going to permute my input vector X. I'll run the optimized code, and then I'll have to unpermute the vector Y. So that has a whole bunch of extra permutations every time I do a sparse matrix vector multiply. Turns out I don't have to do that. So let's suppose I want to solve AX equal B. Then it turns out that what is my permuted matrix? I can write it as this permutation matrix transpose times my original matrix times that permutation matrix. I never actually write down the permutation matrix. It's just stored as a list of indices as a transposition. So now what do? I take my input matrix B, I transpose it once, I solve this system of equations using sparse matrix vector multiply for a permuted solution vector, so no more permutations there. And when I get the output, I permute one more time to get the true solution vector. So I only have to do 2 permutations. Eigenvalue problems are even better. So let's suppose I want to do AX equal lambda X. A and AP, look at how they're related. They're similar matrices because P equals P transpose is the same as P inverse. They have the same eigenvalues. I don't have to do any permutations at all if all I want are the eigenvalues. And if I want eigenvectors, again, I just compute the eigenvectors of AP and do 1 permutation on the output. So these kind of optimizations are going to change higher level algorithms too later, and I'll tell you about that. But are there any questions about this? Yes, microphone?
Do people ever do algorithms where rows and columns are permuted differently?
Yes, we could do that. That would mess up your eigenvalue problem. I couldn't factor them out because I wouldn't have similarity anymore. But certainly for solving a system of linear equations, I could permute the input vector B and the output vector X differently, and that would be fine. So yeah, so that would be a case where that works. Now, if I have an algorithm that depends on symmetry, for example, the conjugate gradient method, I don't have that freedom. If I have an algorithm that does not depend on symmetry, like GMRES, which I'll show you later, then you're free to do that. Okay, another question.
So I generally think that TSP is like very slow to do? Is that not a problem?
So the traveling salesman problem is NP complete, one of the many NP complete problems we have. And so we're only going to do a very rough approximation and just take a few steps. And that's good enough to make a little improvement. Solving it very carefully is not necessary at all. We use a simple greedy algorithm. Okay, so let's go on to multi-core and ask how this all gets tuned for that. So I'm going to show you data on a bunch of different machines because which optimization is best depends on the platform. So there's going to be a Intel multi-core Clovertown, an AMD Opteron, a Sun Victoria Falls, and a now fairly defunct machine, an IBM Cellblade, which shows up in a lot of games. Now, it's all color-coded to tell you what the architecture looks like. So the orange are the cores. So that's where the work gets done. And here you can see there are 2, 4, 6, 8, 8, 16, and 16. Now the blue are the caches. And you can see that there's different, sometimes they're shared and sometimes they're not shared. And the green is the DRAM. And you can see that sometimes there's basically the same path from the cores to the cache to the DRAM. So no matter where you go, it's going to take the same amount of time. Over here, that's not true. If this core wants to go to DRAM, it's much faster to go to this guy than go over that additional network to go to that guy. That's going to be called non-uniform memory access, and that's going to lead to different optimizations. And so let me now tell you a little, so that's the basic architectures, but there's some other differences that I want to highlight. So these that I've colored in here, these have conventional cache-based memory hierarchies. So when you do a load, it asks, are you in L1? If not, are you in L2? If not, are you in DRAM? The usual way caches work. Now on the Cellblade, only some of the processors work that way. I've whited out the ones that are not that way. So there are these two control processors that behave just in the normal way. But the ones I've whited out, and those are called the PPEs, and these guys are called the SPEs. These are local store-based memory hierarchies. For these guys, there are explicit instructions that say, please get the data out of DRAM and put it in my local memory, or please take it out of my local memory and put it back in DRAM. It's more like MPI programming. And so that's where, and there are 16 of those, and that's where most of the work is really going to get done. You have to parallelize across those. So there's another kind of thing that's going on here. This processor, the Sun Victoria Falls, only it has something called chip multithreading. So on all the other ones, the best way to think about it is you have one thread per core. And so here you have 8, you have 8-way parallelism, and that's the best way to think about it. That's not true in the Victoria Falls. Here, the hardware lets you create, and it manages for you multiple threads per core. So the idea is you're running down one thread and you're executing it, and all of a sudden you get to a load instruction from memory. The hardware says that's going to take a long time. I'm going to swap that out in one cycle and automatically do the next thread that you've told me that's available. And then when the first thread, when that load comes back, I can pick it up again. And so it can switch. So you'd think that's expensive. It's the operating system switching. No, it happens in one cycle. The hardware does it for you. And so it can sort of hide a lot of the memory latency. So how many threads are there on these machines? On these, there is exactly one thread per core, so that's the easiest way to think about it. And here I'm just talking about the SPEs, of which there are 16. But on this platform, there are 8 threads per core. So the hardware can keep track of 8 of these hardware threads and switch between them. So there's a total of 128. So to use that platform well, you have to do 128-way parallelism, even if only 16 will actually be executing at a time. So I also mentioned the non-uniform memory access. So in these guys, the DRAM has different speeds of connection. So going from that a load instruction there to that DRAM goes fast, to that DRAM has to go over this extra network, it's slow. So that's non-uniform memory access. That's true in these 3. On the Intel, it's all uniform because there's one common path to the memory. So just a few more numbers. What are the peak speeds of the machine that we're not going to get close to for sparse matrix vector multiply, but they're the peak speeds of the machine. If you use all the processors at full speed, doing local independent matrix multiplies, say, and so there's a big range. And here are the speeds of memory, just so you know what the limits are if you wanted to build your own model, roofline model or something. And what's interesting is that writing is slower than reading. That's going to be increasingly true in future architectures. It's already true in your flash memory that you may have in your laptop, and there's a whole bunch of other kinds of new non-volatile memories that are coming out where there can be very large, this is just a factor of 2 difference, but much larger differences between read and write speeds. So that's something else to think about. So now I'm going to tell you the story about what happens when we apply all the different different optimizations to these different platforms, which one is important for which one. And so I'm going to summarize some results that appeared in this 2007 paper, and you can look up there for details. So I need a bunch of test matrices, so I'm going to pick 14 different real-life matrices, and they're all going to be bigger than the caches, so that you don't have to worry about them fitting in cache, and the memory accesses go away. We'll always do a dense matrix, always pick that one to see what happens. Then there's some well-structured ones in the sense that they're finite element matrices with blocks in them, so we expect to be able to take advantage of that. Then there's sort of a hodgepodge of different things. Some of them are finite elements, but there's no nice simple structure the way there was before. And then there's one that's thrown in because this is the one that's going to benefit from this is the only matrix that will benefit from cache blocking. And I'll explain why later. So a very short, fat matrix. And so how are we going to parallelize? We're going to do it in the obvious way. We're going to break it up into rows. Each processor will get an independent subset of the rows and do local multiplies, and there'll be communication to do X, but there'll be no communication required to share entries of the matrix or to share entries of the solution vector. So but we have to load balance, and we're going to use a very simple load balancing scheme, which is that each processor is going to get not an equal number of rows, but an equal number of non-zeros, because that will balance the number of floating point operations, so denser rows will count as more work. So let me show you the baseline performance on all these different platforms, and then I'll start adding optimizations, and we'll see how much better we do. So here are the 4 platforms, Clovertown, Opteron, Victoria Falls, and the Cell Blade. Now, caveat, the Cell Blade, I'm only going to show you the data at the beginning on the 2 PPEs, which have the usual cache-based memory hierarchy, because the other ones run differently, so I'll show you them later. And the horizontal axis are all the different matrices, starting with a dense guy and moving all the way over. And then I have the median at the end to show you the speed up. And the vertical axis is gigaflops per second, so up is good. And the purple at the bottom, that's the naive code, so sequential. So that's kind of the baseline. And the blue is the naive parallel code, where I just load balance each block row and hand it out to a different processor, and I don't try to do any of the optimizations that we're about to do. But it's sort of the obvious thing to try. And the question is, does it work? Yes, it goes a little bit faster. How much faster should it go, right? This has an 8-core machine. Do I get an 8-fold speed up? Nowhere close, right? So, there's a lot of benefit to be gained. This should also be giving me 8x, potentially. This guy, well, 128, not quite. But it's far below 128. You have to take my word for it there because of the scale. And there it's not doing very well either. So let me tell you what the optimizations are. They're going to reflect the architecture that I showed you. So the first one is NUMA, taking advantage of non-uniform memory access. So in that case, what I want to do is make sure that if a processor is working on a submatrix, that submatrix is stored in the nearby memory. Now, how do I do that? That's kind of processor or, let's say, local programming system dependent. So one thing you can do is every processor mallocs some space, and the malloc is designed to work in its local memory, and then you just put that submatrix there. Some processors work that way. Other ones have the property that the first touch gets it. So everybody sort of touches that memory that they want, a different piece, and that will then, by design, get stored in their local memory. Every processor is a little bit different, and the paper describes the details. Then there's prefetching, and some of these machines also have special instructions that say, please go start getting this data out of DRAM before I need it. And there's sort of special hardware instructions, and there's pragmas that you insert into your C code that will do that for you. And you can prefetch the values, the indices, all that other stuff. And we're going to do exhaustive search on the prefetch distance, because the instruction says, please get me 2 words, 4 words, 8 words, 16. We'll just try them all and pick the best one. Then there is a generalization of the register blocking, and I'm going to call that compression, just for lack of a better word. So it's compression because if I take an 8x8 block and store it as an 8x8 block, instead of having 64 column indices, that's compressing the data structure. But there are other things that we can do. So for example, if I take a submatrix because I'm blocking it, and each processor gets a smaller piece, I may not need 32-bit integers to tell you where everything is. It may be that it's such a small submatrix, I can get away with 16-bit integers in order to store the column index, because I can say that's relative to where I know the beginning of the matrix is. So that will also save space. And the other thing is if I'm assigning a block of a matrix to a processor, even if the matrix has something in every row and every column, a submatrix may have a lot of empty rows just because of its structure, because I'm only giving you a subset of, let's say, the rows and columns. In that case, the usual block CSR format is not good, because remember the data structure, it has a pointer to the beginning of every row, whether it's 0 or not. And so if I have a lot of 0 rows, there's a better data structure where I just store the row index for each non-zero row. And that's going to make a difference. So that's all comes under the heading of matrix compression. And then there's cache blocking. So in other words, I'm going to do not just that one-dimensional partition, everybody gets a block of rows. I'm also going to block it by columns. They're going to be these rectangular subblocks. Now, and that's going to be particularly important for the matrix, the LP matrix, which had just a few rows and a zillion columns. And the reason there is that if I don't break that up, then I'm going to need the whole X vector on every processor. That's going to use up the whole cache, and I'll get all these extra cache misses. So what I'd like to do is say that each processor only needs to multiply certain columns of the matrix times X, and I only need a subset of X, and that's less cache memory needed. Okay, so now let me start adding all of these optimizations in. And so here's the same 4 processors, the same 14 matrices, the median performance at the end, vertical axis is gigaflops, so up is good. And I've color-coded how much faster it goes every time I add another optimization. So I added these optimizations kind of one after the other. So the first thing that we added was NUMA. So that gave the light blue line, and that went that much faster. Then we added prefetching. What color is that? Light green, so that added that little blurb. And then finally, at the very end, we did compression, block CSR, and that added the yellow stuff at the top. Now, there is no NUMA on Clovertown, so there is no little green patch there. But you can see that it all made a difference, and using all of these, went significantly faster than the original speedup. So, and which one was most important depends on the data on your particular sparse matrix, so that's why you would like to have an auto-tuner to try them all. So let me now add one more optimization, and I'm also going to change the vertical axis. So notice the vertical axis here is 8 gigaflops in all of them. So now I've just made it 16, you'll see why in a moment. And I've added one more optimization, which is cache blocking, which is where I'm breaking up the matrix into rectangles instead of just block rows. And the only matrix in which it made a difference was the linear programming matrix, the very short, fat matrix, for the reasons that I told you. You can't afford to keep the whole vector X in cache. And that made a significant difference. So now, finally, I'm going to use not just the 2 PPEs on the cell blade. I'm going to show you how much faster you go when you use all of the 16 SPEs. And this is all hand-coded specially for that machine because it's not a regular cache-based hierarchy, and that's how fast it goes. So that one actually won. But that's all hand-coded stuff that's very specialized to that particular machine. And it's not around anymore. So what is the final speed up that you get compared to just writing the most naive parallelized code? Those are the best case speed ups that came up. So the top of those bars compared to the naive parallel code. And so that's all worth doing. So in fact, are there any questions about this? So in fact, it's worth doing enough that we have built an auto-tuner that we have released, and this is work in progress. So I'd like to tell you what the architecture is of this auto-tuner. Now, I told you about OSCI before, the Optimized Sparse Kernel Interface, whose symbol is, of course, the Cal-Bear mascot, whose name is OSCI. And so POSCI, the parallel version, is naturally 9 of them in this little rectangular square. And so what POSCI has inside of it is all the optimizations that were done, the sequential code that I told you before. That was released quite a long time ago. So it does all the register blocking and all those sorts of things. And this does the parallel optimizations on top of it. This, as I said, is work in progress. And there's lots of class projects and, and other problems going on. So OSCI also does a H transpose times A. It solves triangular systems. Right now, the parallel version only handles sparse matrix vector multiply. There's lots of things to do. So let me give you kind of a tour of how this thing works. and both for the purposes of saying how do you software engineer an auto tuner, and also in case you want to use it and to suggest projects. So it does the register blocking, it does thread blocking, it handles OpenMP and P threads and something called thread pools, so because there's different styles of parallelism, they're all in there. It'll do SIMD, so it'll automatically try the SSE instruction set in all the different ways that you can imagine. It does software prefetching, tries all the different prefetching distances. It does software pipelining, it tries all the unrolling for all the little blocks. And it does the NUMA stuff that I told you about. And we've set it up so that you can build, and since we don't pretend that we're going to ahead of time imagine all the possible optimizations, it uses an embedded scripting language. So it has its own little DSL inside, domain-specific language, so that people can easily, we hope, add new optimizations or new descriptions. It's a language called Lua, which has been around for a long time. In fact, if you've ever played Angry Birds, that's how it works inside. So Lua is a scripting language for all sorts of games. And it's just easy to sort of write down, here's the list of optimizations for this particular matrix, and store that in a database, and so you can add new ones easily. And here are all the other things that you could imagine doing that aren't quite in there yet. So what's the architecture to make all this work? So here's kind of a high-level picture of what it does. And I'm going to break it up into the offline stuff that you can take a while to do, build a database, and then what you have to do at runtime when you look it up to make a quick decision. So offline, what you're going to do for each target architecture is generate a lot of different code variants. And the code variants are going to depend on the R by C, the block size, of course. They're going to depend on the prefetching distance, 1, 2, 4, 8, whatever. And they're also going to depend on how you use SIMD, because you could imagine doing it row-wise or column-wise, different lengths, so all of those are tried. Then that is benchmarked. And then in a database, what you store is for each value of R and C, because you don't know which one you'll need, you store the best variant. You store the 8x8 code that has the best prefetching distance and the best SIMD implementation. So that's all available. The green says this is what you do, and these sort of cylinders are databases that are built. And there's this Lua language inside to make that work. So what happens at runtime? The user supplies a matrix, and then maybe some hints. I'll show you what hints you can give. And then the matrix gets partitioned. So the simplest thing is that it's broken up into block rows so that every processor gets an equal number of non-zeros. Then for each of those block rows, for each submatrix, we do the tuning process. Each submatrix can be tuned differently. So we have these models that we build to sort of estimate the performance as a function of which R and C you chose, and I talked about that in the context of OSCE. Then we'll select the data structure and the code, and we will reorganize it all, and we'll hand the user back a nice little handle, just a name of your tuned matrix, which knows everything you need to know. You don't have to look inside. It knows the data structure. It knows which code to call. And we also can store in a history database what it was. So tomorrow you can say, this is my matrix number 37 from last week. Just do the same thing, and it'll do that automatically for you. And that's stored in an SQLite database. So I think that this just says in words everything that I just did describing the previous page. So a few more points. We use Python as a code generator. So all of the different variants of the code are generated in this high-level language, and then before we do tuning. Just to recall, the non-trivial tuning cost, right? It's going to cost us in the order of 40 matrix vector multiplies at runtime to do this tuning. So the system is going to be designed to not, tune every time, you do a sparse matrix vector multiply, and I'll show you how that works. So what I'm going to do is start with the simplest code that most users would begin with, and how you change it to use POSCE. So here is your basic code, and which doesn't do any tuning yet. So I declare my data structures, and let's suppose I'm just using CSR format. So I have an array of which points to all the values. So there's my array of non-zero matrix values, my array of indices, and my array of pointers to where each row begins. And then I also have my x and the y. So those are going to be the vectors that participate in the matrix vector multiply. And then somewhere in my code, I'm going to do 500 matrix vector multiplies, calling my favorite matrix multiply routine. That's what I want to tune. So that's my starting code. The question is, what do I have to do to modify it to go fast? So the first thing I'm going to do is add a few lines of code. The first one is going to call POSCE init threads. So this is just at the beginning. It's like MPI init. POSCI looks up, figures out how many threads it has available to it, and keeps track of that. And what and it'll, in principle, deal with OpenMP or pthreads or whatever you have. So that's going to be, used later, and then at the end you uninitialize it. So now the next thing I do is I do POSCI create matrix where the input format is CSR. So the input to this is your CSR matrix, the simplest possible format. And what it returns to you is this object, which hides all the details. That's your matrix A, which is tunable. Right? I haven't tuned it yet, but it's a tunable data structure which has all of the information that you need. So you pass in your sparse matrix, and you pass in how many threads you have. And you can also pass in all sorts of hints. Is my matrix symmetric? That sort of stuff. You can just put triangular, all sorts of hints. Then you also need to create a sort of a wrapper around your x vector and y vector, so that because those may get tuned too. And so that tells POSCI everything it needs. I haven't done any tuning yet. So let's keep going. So then what I do is I change this call to my matrix multiply to POSCI matrix multiply. I pass in my object, my tunable matrix. I tell the OSCI, am I multiplying by A or A transpose? This case is I'm multiplying by A. And then I pass in my pointers to X and Y. Now, at this point, I haven't actually gotten any speed up whatsoever because I actually haven't tuned anything yet. I'm just sort of setting it up, so I'm calling everything is available to POSCI now to do the tuning. So how do I get it to tune? So let me just add a few more lines of code. I left out some from the previous slide. They're still there. So the first thing I can do is I can give some hints. So one hint may be I'm going to call matrix multiply 500 times. That's a good hint that it's worth tuning, right? If I were only going to tune it 10 times, it probably wouldn't be worth it. So if so I don't have to tell POSCI that. It can figure it out itself. But if you know that, that's sort of say guarantee it's worth tuning. You could also say I happen to know that they're 8x8 blocks, if you know that. If not, OSCI will figure it out itself, but you can give hints. There's a long list of hints. Finally, you can say please tune. And so you just call POSCI tune mat, pass in the tunable object, and out comes a tunable object, and all the details are hidden inside. And now when you call the matrix vector multiply, it does the right thing. So that's one way of doing it. Here's the other most naive way of doing it. You just call tune matrix inside the inner loop. So every time you go through that loop of 500 sparse matrix vector multiplies, you call please tune. That seems like a bad idea, but actually it's okay, because what this is smart enough to do is that it's just going to monitor your code for a while. Every time you call it saying, oh, you did a sparse matrix vector multiply with this matrix. Oh, you did another one. And it's going to keep track of that, and finally after 40 or 100 sparse matrix vector multiplies, it'll say it's worth tuning. And it'll just do it for you automatically. So what are some of the speed ups we get from doing this? Here's some examples. And I'm comparing it both to the OSCI code, so that's the sequential but tuned as well as possible on one processor. Now it turns out that Intel has its own tuned sparse matrix vector multiply that runs in parallel. That's the red bar. So that's MKL, Intel's math kernel library. And then there's ours, which is faster. Otherwise I wouldn't be telling you this. And there's the dense matrix and all those different ones, and you can see there's some good speed ups. And the vertical axis is performance in gigaflops. And this is on a 6-core platform with 2 threads per core. Okay, so are there any questions about tuning just this basic operation? Because now I want to sort of work my way up in the stack and say, how do I tune higher level algorithms that use sparse matrix vector multiply? So I've told you about this because there's so many iterative algorithms that depend on it, either for solving AX equal B or eigenvalue problems. But whatever we do, if we only think about tuning a single sparse matrix vector multiply, we're going to be communication limited, because I'm still eventually just going to be able to do 2 floating point operations per non-zero entry. And so if I want to beat that bottleneck, I have to look higher in the stack. I have to look at what I'm doing at a higher mathematical level to do better. So let me think about what are the algorithms that use sparse matrix vector multiply, that do many of them. And there's a whole class of them, and they're called Krylov subspace methods. And they come, and you've probably heard of some of these before: conjugate gradients, GMRES, Lanczos. There's a huge long list. And what do? They all have this common pattern at a high level. They start with a starting guess, some vector, call it x1. They do a sequence of k sparse matrix vector multiplies, so they get k vectors. And what do they do with all those vectors? They form some linear combination of them that gives you the best possible solution for either ax equal b or ax equals lambda x. Now, what does best mean? Well, that depends on the algorithm. Each one of these has its own mathematical notion of best, but what they all have in common is that there's this subspace, space spanned by k vectors. It's called a Krylov subspace, and they take some linear combination. So the main cost for all of these algorithms is typically performing those k sparse matrix vector multiplies, and k is typically quite large for solving a large sparse problem. And so what I would like to do is reduce the cost of k sparse matrix vector multiplies. So here's my goal. I'm going to tell you the goal in the parallel case versus the sequential case. So in the parallel case, what is the cost going to be? I'm going to measure it. The improvement is actually going to be in the latency, in the number of messages. So at each step of this algorithm, I'm going to do a sparse matrix vector multiply and some dot products and some Saxbys. That's what's in the inner loop. So each iteration is going to cost at least one reduction. How much is a reduction? It's log p messages. So the classical algorithm will do k log p messages. The new algorithm will do log p messages. It's going to be independent of how many steps you take. So it's going to cost you as much as one reduction. That's a lower bound. You have to do at least one reduction to take k steps. What about the sequential case? In the sequential case, the cost is going to be the sparse matrix vector multiplies. Every time I do this, if A is so big it doesn't fit in cache, I'm going to have to read it from slow memory to fast memory, and from DRAM to cache. And I'm going to have to do that k times to do k sparse matrix vector multiplies. These new algorithms are going to read the matrix once and take k steps. Reading the matrix once is an obvious lower bound, and so this is going to require a complete reorganization of the algorithm in order to be able to do that. Now, this will not work for arbitrary matrices. There's going to be some assumption that comes up, and I'll show you pictures right now what that looks like. It's going to work when the matrix can be well partitioned, so imagine running a graph partitioner, and there's a low surface to volume ratio, so that graph partitioning works well. There are not many edges connecting the different partitions. But I'm going to need that both in the parallel case and the sequential case for this to work. So let me draw a picture of the simplest possible non-trivial case where I can put down every last detail, and it's going to be a tridiagonal matrix, right? Because we all know what that looks like. And what I'm going to do is show you how to compute this matrix powers kernel. So I'm given x, and I want to compute ax, a squared x, a cubed x, dot, 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 a to the kx, and touch the matrix A once. Right, so these are going to be the k vectors that my eventual Krylov subspace method is going to use. And so, my k sparse matrix vector multiplies are going to get replaced by one call to this guy. So here's a picture. This is simple enough I can draw every last detail. So each of these, and I'm going to do it for a 32 by 32 matrix, and I'm going to just do k equals 3. So I'm going to be given x, I want to compute ax, a squared x, and a cubed x. And each of these dots represents a number that I have to store. And so I'm given all these, the bottom row of dots, and I want to compute all the others. So since my matrix is tridiagonal, the question is what depends on what? And here is the simple dependency graph. So since the matrix is tridiagonal, that entry of a times x depends on those three entries of x, right? So that means, so what does a tridiagonal matrix look like? There's somebody on the diagonal. So a sub 3, 3 is non-zero, so I need x3. And it also needs the neighbors to the left and the right because it's a tridiagonal matrix. So to make my art a little bit easier, I'm just going to fill in that triangle. And so as we go forward, everything at the top is going to depend on everything at the bottom of the triangle. And this picture repeats itself everywhere. So for example, that entry of a cubed of x depends on those three entries of a squared of x because it's still the same tridiagonal matrix. And now if I continue those dependencies down, these entries of a squared depend on certain entries of a times x and so forth. And so eventually, everything at the base of that triangle is needed to compute that particular entry of a cubed times x, just by following the triangles down. So there's 7 guys at the bottom, all of whom are needed to compute that one entry of a cubed. And of course, I don't want just one entry of a cubed. I want a bunch of entries of a cubed. So if I'm going to have, for example, one processor compute all of these guys at the top and everybody else, he's going to need eventually everybody at the base of that trapezoid. So the question is, how do I use this? So I've now shown you enough of the general idea of dependencies. Now let me show you the sequential algorithm, which is going to be optimal. So here's the idea. Suppose that I have only enough memory in my cache to store about a quarter of the matrix and a quarter of all these vectors. What am I going to do? Well, I'm going to read in the first quarter of the entries of x. I'll read in the first quarter of the rows of A, and then I have everything I need to fill in everything in that blue trapezoid, right? And I'll just do it once. So now, what's the next step? I'm going to move over sideways, and I'm going to do everything that in this red parallelogram. I'm going to read in the next quarter of the entries of X, the next quarter of the rows of A, but I have to save something, right? Because this guy, for example, depends on him and him. So I have to save those two entries. I also have to save those two entries. So I have to save two diagonals, just sort of like two ghost zones, if you like, from the previous iteration in my fast memory. And I also need to save that row of A, that row of A, and that row of A. And then I have everything I need to compute, to fill in that red parallelogram. And then I do the green parallelogram. And then I do the yellow trapezoid at the end. And I've read in the matrix A exactly once. And I've read in X once. And I've written out the answers once. Right? So that sort of minimizes all the memory traffic for the sequential case. So now let's do the parallel case. So suppose I have 4 processors, and I'm going to assign each processor to compute everybody in this rectangular subset of the dots, right? So processor 2 is responsible for all those entries of AX, A squared X, and A cubed X. And so let me just draw the trapezoid that says what depends on what. And so there's what processor 2 would have to know. So what would the classical algorithm do? Well, the classical algorithm would say, well, processor 2 needs to compute him, so he needs to have a message from processor 3 to get that guy, because he depends on those 3. And in the meantime, processor 3 is going to get data from processor 2 so he can compute him. That's the first message. Then the second step, this processor says, I need you. I'm going to get another message with my neighbor. And then up here, third step, I need a third message with my neighbor. So to compute A squared, and A cubed, I need 3 messages. So here's the obvious way to fix that. I'm going to collect all of this information in one message, in one fell swoop, and send it in a single message from processor 3 to processor 2, and vice versa. Then processor 2 has all the information he needs to compute redundantly these triangles on the side, plus everything that he's responsible for in the red rectangle. So everything in this triangle is going to be redundant work. That's the price I'm going to pay for minimizing communication. I'm going to do some extra communication. So let me just draw all of the patterns. So what's processor 1 going to be responsible for? He's going to do everything in there. Processor 2 will do everything in there. Processor 3 will do everything in there. Processor 4 will do everything in there. And if I put it all together, here's what everybody's computing. And these are the triangles at the ends that are done redundantly. So everything in these triangles is going to be computed twice by the 2 neighbors. Now, is that a bad thing? Well, suppose this is not 32 by 32. Suppose it's n by n. And suppose I have p processors. Then how many redundant flops am I doing? It's k squared, roughly, flops to do that. And that's compared with the k times n over p flops it does to do the rectangle that I have to do. And so as long as k, 3 in this case, is very small compared to n over p, my fraction of the matrix, this is a trivial amount of extra work. And communication is so much more expensive than computation, it's worth doing. Okay. So I should say this picture, the oldest reference for this particular picture is a paper from 1963. And that was, in the case of disk and core, right? People were worrying about it then. But it generalizes. We don't want to do it just for tridiagonal matrices. We want to do it for general matrices. But are there any questions about this before I do the completely general case? So here is a picture of how it works in the completely general case, at least for a symmetric matrix. So each of these, so I've drawn the graph because it's easier to think about the graph of the matrix. And so each vertex represents a row or a column. And each edge represents a non-zero. We've seen this picture before. And I've partitioned it already. These orange dotted lines represent, processor 1 owns that, processor 2 owns that, and so forth. So now let's just think, what does processor 1 have to do in order to compute AX, A squared X, and A cubed X? So it's the same idea as the previous picture. I have to get some information from my neighbors. How do I know which ones? Well, I follow the edges. So to compute that entry of AX, I need that data, that data, that data, that data, and that data. Right? I just follow all the non-zeros. Each edge is a non-zero in a row. And if it crosses over from the processor boundary, I need to get that information. So that means that I would need to get the red edges to compute A times X. Now what about A squared? Well, I just follow one more edge. I do one more step of breadth first search, and I look out 2 edges and I get all the green ones. I need that information in order to compute a squared x. I'm sort of making the triangles wider. And if I want to do a cubed x, I follow 3 edges out and I get all the blue guys. And and then I have enough information for this guy to compute a cube times x. So at each step of the algorithm, I'm going to go out and do 3 steps of breadth first search. Well, that's pre-processing. I'll identify the red, the green, and the blue, pack them into one message, and send them to the guy in the middle, and then he has everything he needs. Question? Microphone?
If the matrices are too big to store in one processor on one machine, how does the graph get analyzed or created?
So this is the graph partitioning problem that we talked about before, and all of that technology can be used here. And as I said, it's such an important problem, let's not reinvent that. There are all these parallel graph partitioning algorithms that are available for us to use that deal with matrices that are so big they have to be distributed in the first place. So there's the parallel algorithm. And as I said, if we're tridiagonal, I just sort of did the obvious way of blocking. In this case, I have to do graph partitioning using one of those algorithms. And in fact, it's actually better to do hypergraph partitioning. That's the thing that I introduced at the end, because if this matrix is non-symmetric, then it's much more important to do hypergraph partitioning to get the right partitioning. So the other thing, so that's good enough for the parallel algorithm. Now what about the sequential algorithm? Let me go back here and just look at what this was involved. So I had to choose, here I made the choice. I went from left to right, or the top of the matrix to the bottom. So what do I do in general? It's not obvious what left to right means, top to bottom, for a general matrix. So what do I have to do? I have to decide in what order I'm going to process each of these orange surrounded regions, right? That's the sequential algorithm. I'm still going to partition it. The question is, in what order do I do it? So what's the criterion? What I'd like to do is, let's suppose I do this guy first. Then what I'd like to do is leave as much information left over in cache so that the next block that I do can reuse it, right? That was leaving the 2 ghost zones behind, the 2 diagonals in the tridiagonal case. So for example, would it be a good idea if I first did all those guys and then came over here and did all those guys? No, because I wouldn't leave anything useful in cache. So the question is, in what order should I process all of these partitions so that I leave as much information behind in the cache that I can reuse? That's the traveling salesman problem again. So what I'm going to do is I'm going to build a graph where there's one vertex for each of these partitions, and I'm going to have an edge which says how much useful information is left behind if I do him and then him. And what I want to do is do an order, travel through all these partitions, that's the traveling salesman problem, in an order that maximizes the amount of useful stuff left behind. And again, so that's an interesting optimization that we can solve approximately. So having done all that, in theory, what are the speedups in practice? So let me show you. So here is an example on Intel Clovertown, and there's a whole bunch of different sparse matrices, as I've shown you here. And the vertical axis is performance, so up is good. And the red bar is the best optimized single sparse matrix vector multiply, using all the tricks I was telling you about before. And the green is how much faster you go if you're willing to do multiple sparse matrix vector multiplies. And so you can see there's big speedups. It's labeled at the top by what the optimal value of k is. So the picture I showed you before, I chose k equals 3, just so I could draw the picture, but that's a tuning parameter, right? I want to pick k to go, well, here as fast as possible. And so for this matrix, which is almost tridiagonal, it's a 5-point stencil, so it's actually pentadiagonal. So it looks almost the same there. It's worth taking 50 iterations, going up to 8 to the 50th times x. And that gave us a speed of 6.4. For this matrix, which isn't nearly as not easy to partition, I only wanted to take 4 steps, and it only gave me a speed up of 1.3, and you can see all these k's are labeled there. Now, this optimization, so this was an Intel Clovertown, that's an 8-core machine, actually used both the optimizations I told you about, both the sequential and the parallel, because there's 2 sources of communication. There's on-chip, off-chip, that's the sequential optimization, so I used the sequential trick. And then once I got a bunch of stuff on the machine, I have 8 cores. They communicate with one another, so I used the parallel optimization too. So this was a hybrid of using both kinds of optimizations to get these speedups, because machines are are that way. So here are some of the results, just to summarize. So on the Clovertown, the speed up was up to 6.4. So we also measured some out-of-core speedups. So that is where it's too big to fit in DRAM and it actually has to go to disk. And there were speedups in the order of 3. And these were just using our performance models and counting communication and so forth, because we didn't actually build this. That's another interesting class project. So we had this model of a petascale machine, and we had models for how fast it communicated. There was a speedup of 6.9. And this one we picked just for fun. So what's the grid? There's a different computer in every city, connected over the internet. That's a really big latency. It's not clear you'd ever want to do that, but there reducing the latency gave us a speedup of 22, just for fun. So, so anyway, as I said, the multi-core results use both the sequential speedup and the parallel speedup. Okay, so that's going to be, so that's a good idea, but the trouble with this is that this is not what conjugate gradient uses. It's not what GMRES uses. It's completely different. And so what I need to do now is say, well, since I know that I can compute these vectors really fast, are they useful? Can I reorganize all of those higher level algorithms to take advantage of these big speedups? So that's the next step. So let me just remind you about these algorithms. And so for either solving AX equal B or eigenvalue problems, they all start with some starting vector, and they do k sparse matrix vector multiplies. And they do, but they're not the same ones that I just did. They're different ones. But anyway, you get this vector space, which is spanned by k vectors. And then you find the best linear combination of those k vectors, and that's your solution. And the definition of best depends on whether you're doing conjugate gradient or GMRES or whatever. So what I want to do is get the same theoretical speedups for these methods that I just got for this kernel. So what does that mean in the parallel case? I want to take k steps of conjugate gradient, and instead of doing k reductions, which cost me k log p messages, I want to do log p messages. That's going to be optimal. So I want it to cost me 1 reduction. Just talk to my neighbors, as seldom as possible. And in the serial case, the conventional algorithm, k sparse matrix vector multiplies. I'm going to move the sparse matrix from DRAM to cache k times. I want to move it once, and still take k steps of the conjugate gradient method. So there's going to be lots of speedups that I'll show you, both measured and modeled. It turns out that if you do it in the obvious way, it's completely numerically unstable and you get garbage. Even though it's the correct algorithm in exact arithmetic, it's garbage in floating point. So part of the design space is choosing the right version to get the right answer in the real world, in floating point arithmetic. Now, some of these, so there's a lot of work on this. And again, people thought about this a long time ago, but they kind of were defeated by the numerical stability and they gave up. And so that's been cured recently. So let me now tell you how it works for GMRES. And so here is how this algorithm works. I'm going to compute a basis of this Krylov subspace. So I'm going to start with a vector B, and I'm going to find some vector in the space spanned by those that minimizes the residual, right? I'd like to solve AX equal B. So I'd like to make AX minus B as small as possible. And what GMRES does is it computes a bunch of vectors and chooses the x in the space spanned by those vectors to minimize that residual. So I'm going to start by just reminding you of what the classical algorithm is, and I'll tell you the new algorithm. So standard GMRES starts with a vector. It does a matrix vector multiply. So there's the SpMV. And then it runs an algorithm called modified Gram-Schmidt. It takes that vector that it just computed and makes it orthogonal to all the previous vectors that it computed. So if you studied Gram-Schmidt, right, I'm going to take a dot product of W with V naught and subtract a multiple of V naught from W to make them orthogonal, and do that for all of those guys. And so the output of this will be the next orthogonal vector. And then I keep track of a bunch of other dot products. This is going to be a little k by k matrix. And when I'm done, I'm going to solve a little tiny k by k least squares problem with this matrix that I've computed in the middle. So what's the complexity of doing this? I'll tell you sequential and parallel. So I have a loop. I'm doing this k times. So I'm going to do k sparse matrix vector multiplies. So if my sparse matrix has NNZ, number of non-zero entries, I'm going to have to move it from DRAM to cache k times. So the bandwidth cost is k times number of non-zero words moved. And then the modified Gram-Schmidt, it turns out I have to to do this, I have to do k squared dot products in Saxby's, so that's going to be k squared times n, because it's an n by n matrix. In the parallel case, I'll have k sparse matrix vector multiply, so that's going to be k times I have to talk with my nearest neighbors and exchange information. And then my dot products, again, k squared dot products, so that's k squared reduction, so k squared log p messages. So here's the new algorithm. And it's going to use not just the algorithm I just told you, it's going to use an algorithm I told you last week. So I need to do both a better sparse matrix vector algorithm and a dense matrix algorithm. So I'm going to call that kernel, that's called, or we call it the AKX kernel. There's my starting vector, and I compute all of those guys, and I put them all together, and I pack them into this matrix whose dimension is n by k plus 1. I still need to emulate this algorithm. I need to get a bunch of vectors which are come from orthogonalizing the columns of this matrix. So, but I don't want to run modified Gram-Schmidt, that's too expensive. What I really want to do is the QR decomposition of this tall, skinny matrix with n rows and k plus 1 columns. So I want to factor it into tall, skinny, orthogonal matrix times a little triangle. That's the tall, skinny QR algorithm that I told you about very briefly when we did the dense linear algebra lecture. So the output of it, and this also minimizes communication, and out comes the same set of vectors here, q, that we called v's over there. It turns out you can still build this little k by k matrix from that R matrix, solve the same least squares problem, and you're happy. So what's the cost here? I'm going to do, in the sequential case, as I said, if A is well partitioned, then I only have to read A from slow memory to fast memory once. So the number of words moved goes down to NNZ, so it's a factor of k times faster, going from there to there. Tall, skinny QR, I only have to touch all the entries in that vector once. It's an n by k matrix, W is an n by k matrix. I only have to touch it once, so it's k times n words moved. That's also a factor of k times smaller, so there's a factor of k speed up. In the parallel case, as I told you, we only have to talk to each processor once, talk to your neighbors once. So instead of k messages, I have one message to compute W. And then the tall, skinny QR is a single reduction operation. But the reduction is a QR decomposition. But now I'm down to log p messages instead of k squared log p. So everything I've told you is completely true in exact arithmetic. And as I alluded to before, there's a problem here. So where do you see that there might be a problem in numerical stability? So there's something hidden in here which is numerically unstable. And actually, everybody in the world almost uses this algorithm every day. It's called PageRank. So this thing here, what is happening to these vectors is I do a times v, a squared times v, a cubed times v. What is happening to those vectors? They're converging, actually. They're becoming more and more nearly parallel to one another. So which vector are they becoming parallel to? The eigenvector of the largest eigenvalue. So every time I multiply a matrix times a vector, I can think of this, they are all converging to the dominant eigenvector. And that's how PageRank worked originally in order to do Google search. So that means that all of these vectors are becoming nearly parallel. Do you think that's a good basis for a subspace if you have a bunch of nearly parallel vectors? That's where all the information gets lost. Okay? So no problem in exact arithmetic, but in the real world, that's a problem. So let me run the algorithm anyway, and let's just see how well it converges or not. So here I have a convergence plot. This is for a diagonal matrix, so it's real, so there's no worries about round off from actually doing A times X. It's a diagonal matrix. The horizontal axis is the number of iterations. The vertical axis is the log of the residual, so convert down is good, it's converging. The black line, or the black dots, that's the standard algorithm, so no problem there. And the blue lines, or the blue dots, are the algorithm that I just showed you. It's not converging very well, is it? So what I'm going to say here is that these blue dots, that's failure to converge, and I'm going to call that the monomial basis, this particular choice. Now, why is that? What I'm doing here is I'm really taking a polynomial in the matrix A and multiplying it by x. I'm doing a times x, a squared times x, a cubed times x. Those are particular polynomials in the matrix A. They're called monomials. But there are a lot of different polynomials in the world, and some of them are better. And if I pick the right set of polynomials, I'm not going to tell you exactly how to compute them. So P1 of A, P2 of A, P3 of A, different linear, quadratic, cubic polynomials. I can make those vectors that were nearly parallel nice and numerically independent, and it converges just fine. So that is part of the design space, that we have to pick the correct set of polynomials in order to have real numerical convergence. And I invite you to, there are a lot of papers on the topic of how you do that. I'm not going to go into it here. So now let me show you some speedups. And so what I've done here, again, for a bunch of different sparse matrices from real applications, I'm showing you the speed of the new algorithm versus the old algorithm. And it's normalized so that the time of the new algorithm is 1. So these are all 1. And this other bar is the old algorithm, and it's higher, so it's slower. And so what I'm doing is I'm taking my highly optimized new algorithm and comparing it to classical GMRES, but I'm doing classical GMRES as well as I can. So the sparse matrix vector multiply in the classical algorithm is the best optimized version we can do. And so you can see there's speedups of 2.3, 2.1, 1.7, and so forth. And part of this is the tuning parameter. How many steps do I take at a time? That's the k. And you can see k is often 5, but it varies. It's a tuning parameter. And what do all these colors mean? The colors tell you which subroutine sped up compared to which other ones. Because remember, I'm doing both sparse stuff, sparse matrix vector multiply, and I'm doing dense stuff. I'm doing QR decomposition or modified Gram-Schmidt. And it's color-coded by how much time each part took. And so depending on the matrix, either the dense part was the bottleneck and speeding it up was the most important, or the sparse part was. So let's just look. So here the purple is modified Gram-Schmidt. And so that's the unoptimized dense linear algebra. And that shrank down to the yellow plus the orange, the tall skinny QR plus some sort of block Gram-Schmidt, which is also more like matrix multiply. And here, again, purple shrank down to yellow plus orange, so that was important to speed up. Now what about the sparse linear algebra? Here, the thing to compare, let me get this right, is the blue. That's the classical one sparse matrix vector multiply at a time, but optimized as well as we can, and that shrank down to the red. So blue shrank to red, blue shrank to red, so it was important to get the sparse stuff right too. Now, I have to tell you that the first time we did this experiment, there was one student who was busy optimizing and very carefully tuning the sparse linear algebra part, and there was a different student who was tuning the dense linear algebra part. They both made them run really fast. They put them together, and it slowed down dramatically. And the reason was that when they tuned them independently and put them together in the inner loop, they fought one another over the cache. Because the dense linear algebra assumed it owned the whole machine and optimized for that. And then the sparse linear algebra assumed it owned the whole machine, optimized for that. And they spent all this time thrashing the cache. Then they went back and said, what we have to do is co-tune it. We have to know that we're calling one after the other, and only then did we get these speedups. So that means that it's no longer possible to independently tune a sparse linear algebra library, independently tune a dense linear algebra library, put them together and hope for the best. It doesn't work anymore. So that's why this class exists, I guess. So you have to sort of tune at a higher level. So let me now just show you eye candy, one more algorithm to show you that the math gets a little bit more complicated. So this is an algorithm called BiCG stab, and this is commonly used for non-symmetric problems. Its advantage over GMRES is that it uses a lot less memory. So if you take k steps of GMRES, it keeps k vectors in memory. This keeps 3 or 4 vectors in memory. So it's much, much cheaper. It scales to larger problems. And here's the classical algorithm. And I'm just going to show you how it changes. So it has some dot products. It has some matrix vector multiplies. And it looks like that. And here, after you reorganize the mathematics, is what the communication avoiding version of it looks like. And I'm not expecting you to read this, but that's what it took to sort of, this is doing an exact arithmetic, exactly the same thing as this. But now what I've done is I've taken this matrix vector multiply, there are actually 2 of them, and they get replaced by 3 calls to this kernel, which computes ax, a squared x, a cubed x. So these are 3 calls to that. And in addition, there are all these dot products, and those get replaced, it turns out, by a single matrix-matrix multiply, by this tall skinny matrix times its transpose. And that replaces all these dot products. And then the rest of the math goes over. Okay? So, and this has now been done for a large number of different algorithms, and there's a large literature not just for GMRES and by CGStab, but you can, these are available. Now, you don't have to take my word for it that this is a good idea. You can take the word of someone at a higher pay scale, so President Obama. And so here's a quote from the Department of Energy budget request from 2012. And so, which is this huge document with lots of details in it about budgets, but there are a few pages in the middle which have research highlights from the previous year. And so one of them was this. It says, on modern computer architectures, communication is much more expensive than arithmetic. So to minimize communication, you have to reformulate the whole algorithm. And it said it's being put into this Trilinos library, which we'll hear about a little bit next time, which is one of these standard packages produced by the Department of Energy that a lot of scientists use to do their coding. And when we first saw this, we went to talk to the head of the Trilinos project, Mike Carew at Sandia National Lab. And indeed, it was referring to our algorithms because he hired the student who did this as a postdoc, and he was putting all of these algorithms that I just described to you into the Trilinos package. So they're all available there now. So this includes both the communication avoiding GMRES that I told you about, and the tall, skinny QR algorithm. Okay. So let me tell you a little bit more about the tuning space for all of these. I've sort of given you dive down into one class, but there's a lot of different things to do. And so I told you about GMRES. I told you about by CGStab. There's also the conjugate gradient algorithm, the Lanczos algorithm, Arnoldi algorithm. There's a large list of these. Some of these are in Mark Homan's thesis. Some of them are in later papers that are on the Bebop webpage. So if you're interested, you can go look at them there. There's also the question of which polynomials do I choose? Because I showed you had to choose the right set of polynomials. There is no closed answer. We know that some general principles for choosing good polynomials that give you numerical stability, but they don't always work. So there's questions there. And then when you try to solve AX equal B, there's something people often do which is called preconditioning. So instead of solving AX equals B, you pick a matrix M and you solve MAX equals MB. And how do you choose M? You choose it so that M times A is much nicer, not as hard to solve, not as ill-conditioned as A. So M is in some sense an approximate inverse of A. And there's a huge, people have been working in this field for many years to come up with good, cheap M's that you multiply it by A and it makes it well-conditioned because M can't afford to be very expensive. And how do you choose M's and then make this particular class of communication optimizations work? We know how to do it for a few preconditioners, but there's lots of open questions, and so that's an open problem too. So the next sort of issue is that for which there are a lot of different ways to represent sparse matrices. And I've talked about one, which is sort of the classical way, but there's actually a whole bunch of them that come up in practice, which I'm trying to represent by this little table. So it turns out, to represent a sparse matrix, what do you need? You need to store the non-zero entries, and you need to store where they are, the indices. Now, if you store them both explicitly, that's the algorithms we've been talking about. That's like CSR format. You're going to have, NNZ memory to store all of the indices and NNZ memory to store all of the non-zeros. And that gives you all of the variations I've been talking about. But there are a lot of sparse matrices that come up where you can, do it a lot cheaper. So in particular, let's suppose you're doing image segmentation. So, and I talked about that particular application. So what does your sparse matrix look like there? Let me remind you. So you have an image, so you have a bunch of pixels, each one has colors and so forth. You have a matrix where there is one row and one column for each pixel. And what do the matrix entries represent? So entry I and entry ij says how similar is pixel I to pixel j? How likely are they to be in the same image in this big picture, right? They're both part of your shirt, or they're both part of the wall. They both belong together. And so the structure of the sparse matrix is that for each pixel, you look at all the pixels that are nearby, let's say within a distance 10, and you say how similar are you? So you know exactly what the matrix structure is. It's sort of banded. It's a little bit more complicated. There's no reason to store the indices because you can build that into the algorithm because you know what pixels are and who the nearby pixels are. All you have to store are the non-zero entries because that depends on what the pixel looks like. And so you can save a large fraction of the storage required by building in the knowledge of the structure. That's true in lots of other codes too. Here's another example where the indices are explicit, you got to store those, but the non-zero entries are implicit. And the simplest example that I've mentioned before, you need it for graph partitioning, is the graph Laplacian. In that case, all the non-zeros are -1s on the off diagonal, and you don't have to store -1. You just have to remember where they are. So that's another example where you can save half or more of the storage. And the one that has the most win is everything is implicit. And you don't have to store the non-zeros, you don't have to store where they are. It's called a stencil. And the simplest example is you have a 2D mesh, and you say, for each entry in my mesh, I want to average with my nearest neighbors. It's the same average everywhere, right? There's no reason to store any indices or any coefficients because you know it's 1/4, 1/4, 1/4, 1/4. And we're going to and that is so common, that's going to come up in another lecture later where we talk about optimizing grid computations, on regular meshes, because that's another one of the dwarfs. So that's the design space that comes up. And but the idea of minimizing communication is what holds it all together. And so we've talked about ax, a squared x, a to the power x. It works for polynomials too. It's pretty much the same algorithm. So another optimization is that you don't want to do it just for a single column. You might have multiple columns. And then for some of the algorithms, you want to do not just ax, but a transpose. So how do you take advantage of that and do both ax and a transpose y and only read a once? That makes perfect sense to do that. And sometimes for the singular value decomposition, it's a times a transpose that you're doing. And for some applications, you need all of these vectors, and for some, you only need the last one. And that way, you can obviously save some communication if you can throw everything away except the very last vector. And let's just say that there's even more variations on it where you can actually interleave the computation of all the vectors and the QR decomposition. You can sort of put them together and do a little bit of one and a little bit of the other and cut the communication even more. So these optimizations go on and on. So let me come to the last slide, which is that we talk about this in detail every week if you want to hear more about it. At the weekly Bebop meetings, they're free lunches from 12 to 1:30 and 380 soda. You can experiment. So one thing that you could do possibly is experiment with sparse matrix vector multiply on different architectures, or you could just use it in your own project. You have a particular application you want to parallelize, just use the available tools and see how well it works. You can try to speed up on particular matrices of interest because some of these optimizations are problem specific. So you may have some data mining problem, or the BiCG-STAB algorithm that I just told you about, that was just incorporated in a bottom solver in an adaptive mesh refinement code at Lawrence Berkeley National Lab, and they got big speed-ups in that. So you may have a particular special matrix that you want to do. There's all sorts of things in the preconditioning world that remain unanswered. We have ideas, but no implementations. Now, it turns out a lot of people have been experimenting with new frameworks to try to generate this kind of code automatically. There's something called the sparse polyhedral framework from Michelle Strout in Colorado, and Halide, which I think is from MIT. So there's a lot of other research in trying to build systems to do this kind of stuff automatically. And so all of those are fair game as tools for class projects. So are there any questions? That's a good place to stop. And we're ready with a microphone. So any questions about the GPU assignment? Do you have enough? Okay. Well, enjoy programming GPUs.